Hello, my name is Amira. In this presentation, my group members and I will be talking about dynamic loads, beam deflection, and column buckling on a high-rise building. In this project, we will be talking about the highest building in Malaysia, which is the Petronas Twin Towers. I'm going to start by talking about the dynamic loads and ways on how to minimize its effect on the structure. But before that, have you ever heard of anything such as the taller the building, the more dynamic load it has to withstand? Well, what is dynamic load actually? Dynamic loads are non-static loads which may cause deformation or failure of a structure. The Petronas Twin Towers going up to 451 meters to the tip has to withstand a very high amount of dynamic load. The dynamic load includes the wind load, earthquake load, and the hydrostatic pressure. These loads vary with time and height. So, let's talk about the different types of dynamic loads to be considered during the design stage of this project and how to minimize their effect. First, let's talk about wind load. Wind is caused by air flowing from high pressure to low pressure. Its direction is influenced by the Earth's rotation. When structures block the flow of the wind's kinetic energy is then converted into potential energy of pressure, which causes wind loading. So for design purposes, wind loadings can be treated either using static or dynamic approach. The challenge that the Petronas Twin Tower has to face gets worse because of the height. Because at a higher temperature, the wind speed gets higher, which means the wind load will exert a higher force and stress laterally on the structure. So in order to minimize undesirable wind effect and structural response in this tall building, the Petronas Twin Towers has developed by far simplest way to reduce the impact of high winds on a tall building, which is through an approach called corner softening. Corner softening sees sharp edges smooth off on the structure to make it more aerodynamic, and then it is small cutouts created on the edges of the structure to scramble prevailing winds and reduce the strength of the vortices they create. Next is the earthquake loads. Earthquake produces loadings on structure through its interaction with the ground and its response characteristics. These loadings result from the structure's distortion caused by the ground's motion and the lateral resistance of the structure. Their magnitude depends on the amount and type of ground accelerations and the mass and stiffness of the structure. So during an earthquake, the ground vibrates both horizontally and vertically. The horizontal accelerations then create a shear force in the column that put the block in a sequential motion with the ground. So if the column is stiff and the block has a small mass, the period of vibration of the block will be short and the block will accelerate with the same motion as the ground, and therefore it will undergo only a slight relative displacement. So the earthquake load of building is the sum of the earthquake weight of the floor. This means it is very crucial for the Petronas Twin Tower as it has 88 floors with 5 floors being underground. Therefore, a proper construction with an equipment minimize the earthquake effect should be taken in consideration while building the Petronas Twin Tower. With that, special techniques are required. The two basic techniques to protect the buildings from damaging caused by the earthquake are the base isolation device and the seismic dampers. The base isolation is to detach the building from the ground in such a way that the earthquake motions are not transmitted up through the building or at least greatly reduced. Meanwhile, the seismic dampers are a special device introduced in the building to absorb the energy provided by the ground motion to the building. Lastly, the hydrostatic and soil pressure. Hydrostatic pressure is defined as the force exerted by the water on the foundation. These water molecules are present in the soil material. In a practical situation where the hydrostatic pressure becomes too large, leakage of water starts appearing from the basement area. This leakage causes cracking and voids in the foundation as concrete is actually a porous material. So the hydrostatic wall pressure is developed due to the consequence of a groundwater pushing against the foundation. This problem could become worse during rainy season, as during rainy season the ground soil becomes oversaturated. So this leads to a high amount of hydrostatic pressure. Practically, there is no way to stop pressure exerted due to excess water. However, there is one way. The effect can be minimized by extracting as much moisture as possible. So the hydrostatic pressure relief technology is introduced, which it aims to keep the foundation of the hydrostatic pressure stable through the changing of the dynamic seepage pressure of soil layer. So in order to control the influence of groundwater rotation on the structural body to keep the basement dry. So it has the advantages of relatively shallow foundation excavation, shorter construction period, lower noise and less material waste and pollution produced during the construction phase. Meaning to say, the hydrostatic pressure relief is one of the ways that could be used to minimize the hydrostatic and soil pressure on a high.
Hi, I'm Layinli. I'm going to explain about question 2, which is sketching the loading for structure given. My question asks for the sketch of loadings and reaction on the members BE and FED, and also the sketch for BE deflection. An appropriate slab thickness T has been proposed. I've assumed that our concrete slab thickness T equals to 200 mm. The load for office and concrete slab can be calculated by the concrete slab density, which is equal to 23.6 kN per meter cube. Office live load pressure equals to 2.4 kN per meter square, which have found the table of minimum densities for design loads from materials and minimum live loads, which can help me to determine the live and dead loads applied on the structure. From the values given, which is A equals to 1.25 meter and B equals to 1.5 meter, I can know that our reinforced concrete slab behaves as a two-way slab from the ratio. These are the calculations and my sketch for the loadings and reactions. The reactions that support B and E are the same, which is 3.89 kN reacting upwards, while the total load along the beam was 8.9 kN per meter. And for beam FED, the total load along the beam was 4.45 kN per meter at both sides of the beam, and the concentrated load, which is acting in the middle, which is EY. The deflection of BE was sketched by estimating the concentrated load is more focused in the middle of the beam. That's all from me, and now we'll pass to the next person.
Hi, I'm Anita. I'm going to be talking about the deflection on the beam BE. So now, there are two methods we're going to use, double integration and moment area theorem. Now, for the first one, double integration, since the loading on the beam is symmetrical, we will get a maximum deflection in the middle of the beam, while at B and E there will be zero deflection, so we only need to find deflection in the middle of the beam at 0.75 meters. Now, to do that, we need to find the moment equation that represents the beam where the deflection happens. This can be done by cutting anywhere in the distributed load that is rectangular. So from cutting there, you can find the moment equation. This moment equation, integrated once will give you the slope, and integrated twice will give you the deflection equation. Now, from these two equations, you can see that there are two constants, C3 and C4, which can be found when at two conditions, which is x equals to 0. So when at point B, V equals to 0, which means the deflection at point B is 0. So x equals 0, V equals 0, and at x equals to 0.75, which is the middle of the beam, dV dx equals 0, which means the slope is 0. From then on, you can find C3, C4, and you substitute it back into the deflection equation, and then you use the value of the middle of the beam to find the deflection at the middle of the beam. The E and I values are 200 GPa for steel, and the I value is going to be calculated as seen on the right side of the slides. The second method we're using is moment area theorem, where you need to find the area under the graph to find the deflection. Now, to do that, you need to draw the BMD diagram. The values of the BMD diagram can be found by substituting the distance for the point you're trying to find into the moment equation found in the double integration method before. Once you find these values, 1.92 and 1.85 over EI, you can find the area under the graph from point 0 until point 0.75, and you can find the deflection.
Hi, I'm Izlan, and I'll be presenting the design factors that affect the lateral stability of the Petronas Twin Towers. The Twin Towers are tall and complex marbles that are extremely massive. Major problems that engineers tend to face with tall buildings such as these are the lateral buckling of the beams due to the extreme load of a massive skyscraper. Beam deflection usually occurs as soon as the lateral load is applied. At any given load level, each floor in the beam moves laterally through a deflection relative to the floor below it. Due to this relative deflection, an additional secondary bending moment, known as the P delta moment, develops in each story. This moment tends to reduce the overall strength and stiffness of the frame, which eventually leads to lateral instability of the beam. Therefore, as we can see, beams are important components in resisting the vertical load, and it is essential that the right design for these beams are chosen. One of the factors that affect the lateral stability of these beams is the shape of the cross-section, either being open-sectioned or closed-sectioned. An example of open-section beams would be the L and I beams, whereas the examples of closed-section beams would be the tubular and cylindrical beams. The buckling of beams is directly proportional to the second moment of area, hence why the beam with the highest second moment of area provides better stability. Besides that, the type of loading that is applied to the beam greatly affects the lateral stability as well. It is important to note whether the load applies a compression or tension on the beam. Lastly, the material of the beam is also important, as different materials have different yield stresses and therefore vary in their ability to withstand buckling. Different materials also have varying amounts of residual stress in the beam, which is inherent in each beam through the industrial stage of the beam's creation. This includes the welding and the melting of the beams. Therefore, it is important that this is accounted for as well. Thank you.
Hi, my name is Faez Hazeem. Now I'm going to present about ways to prevent buckling of beam on high-rise building. So, how do we prevent buckling from happening? Firstly, is to use a high-strength material such as the reinforced concrete. Reinforced concrete is a high-performance concrete which has the strength of more than 40 megapascal. It is also being used because it can build car and transmit load across the building, and it also provides lateral resisting system that makes the structure very stable and hard to buckle. Secondly, buckling can be avoided by reducing the length of the beam, or in other words, we will use shorter beam rather than a longer one, as it is more rigid and hard to buckle. So, why did I say shorter beam is more rigid is because it has more load capacity that makes it having higher strength to sustain load. For your information, length reduction of a beam can increase its strength by 4 times higher, according to Winter 1958. Next is increasing the second moment of inertia by using I-beam or hollow cylindrical beam. The reason we use this type of beam is because the moment of inertia in the cross-section is higher, making it has less tendency to buckle. As we all know from the Euler formula for the critical load, the moment of inertia is directly proportional to the critical load, meaning to say higher moment of inertia will lower the chance of buckling by increasing the critical load. Okay, now, how do we increase the critical load? The critical load can be increased by reducing the effective length. Effective length can be expressed as effective length equal to KL, where K is the effective length factor and L is the actual length of the beam. Okay, now, the question is, how do we reduce the effective length? The effective length can be reduced by providing brace between the two endpoints of the beam. As you can see from the slide, the value of K for fixed-ended beam on both sides is the lowest compared to the others with only 0.5. This shows that it is very stable as it has the most support reactions. Please take note that small value of K will increase the critical load. Last but not least, buckling can be prevented by applying the concept of buckling restraint brace frame system, or well known as BRBF system. This system or concept is mainly designed to withstand cyclical loading such as the earthquakes. So, the reason to use BRBF system is because BRBF system has high level of ductility to undergo deformation without failing. When we talk about ductility, ductility itself is used to designate how well a building can endure large lateral displacement during earthquake, which means high ductility structure is hard to buckle. I think that's all from me. Thank you for listening.